So now that we've learned that neurons actually communicate with each other through a chemical messenger, we have to bring in this important idea of representational information. Representational information, or representation, is when we don't have direct access to the original information. The lack of direct access to other neurons, having to rely on a chemical messenger moving from the presynaptic neuron to the postsynaptic neuron, means that any changes in the chemistry in the synaptic gap can actually cause the postsynaptic neuron to misinterpret what the presynaptic neuron is doing. Remember, the postsynaptic neuron does not have direct access to the presynaptic neuron. It can't tell for sure that it's firing, and instead it relies on these chemical messengers. If the chemical messengers fail to get released, or if chemical messengers get accidentally released, the postsynaptic neuron is going to think the presynaptic neuron has fired, whether it has or not. This means once we move to this form of representational information, this chemical component, we can now introduce falsehoods into the equation. Our nervous system can actually be lied to or confused by the presence of chemicals in the synaptic gap. That is exactly how drugs work. Drugs act to change the neurochemistry in the synaptic gap, causing the postsynaptic neuron to misinterpret whether the presynaptic neuron has fired or not, thus changing our perception. Remember that neurons and neurotransmitters can either be excitatory or inhibitory. Neurotransmitters can work by increasing the likelihood that the postsynaptic neuron will fire, or they can decrease this likelihood. They can either be excitatory or inhibitory. Drugs can either increase the effect of a neurotransmitter or activation of a receptor, or decrease the activation of a receptor for a given neurotransmitter. So that means when we want to ask the question of what is the effect of a drug on our nervous system, we have to stop and ask whether that neurotransmitter or that part of the nervous system, that neurotransmitter is acting as an excitatory or inhibitory agent. Let's take a look at this table. In the rows we have inhibitory and excitatory. Inhibitory and excitatory refers to the effect of the postsynaptic neuron. Is the postsynaptic neuron being less likely to fire, thus inhibitory, or being made more likely to fire, thus excitatory? Then in the columns we have agonist and antagonist. This refers to the types of drugs that we can have. An agonist is something that increases the effect of the drug. An antagonist is something that decreases the effect of the drug. So what I would like you to do is pause this video and try to fill out this table. What would be the effect of an agonist on a neurotransmitter that is being inhibitory? What about an agonist on an excitatory neurotransmitter? An antagonist on an inhibitory, and an antagonist on an excitatory. So pause here, fill out that table, and then unpause and we'll take a look. Okay, so remember, agonist means increasing the effect, antagonist means decreasing. So if a neurotransmitter is being inhibitory, it is slowing down a neuron, and an agonist will increase the effect, right? So an agonist drug acting on an inhibitory neurotransmitter will actually decrease neuronal activity. However, an antagonist limits the effect of that inhibitory neurotransmitter, thus increasing neuronal activity. An excitatory neurotransmitter, however, an agonist increases the effect, thus increasing neuronal activity. The antagonist decreases it, thus decreasing neuronal activity. So an antagonist and an agonist will either increase or decrease a neurotransmitter's effect depending on what its effect was, right? So you have to keep in account, is the neurotransmitter inhibitory or excitatory? Is the drug an agonist or an antagonist?